So welcome to the pre-recording of lecture 11 of Computer Algorithms 1, scheduled for the end of the fourth week in our 8-week summer course. We will start week 5 with our midterm exam, and this lecture is intended to prepare for the midterm exam. Now, the title of the lecture is Review Answers, and I will use the second set of slides. The first set of slides contains the questions, not the answers. In some sense, this set of slides is a lot more useful if you are in a hurry and want to have a very quick overview. But I actually believe that you learn best if there is some struggle. So if you have looked at the review questions and also at the relevant lectures and course materials, and in this way learn something. So um, overlooking answers goes very quickly, but indeed you overlook several essential aspects. Okay, there are two sections in this lecture. I will give an overview of what we have covered, and then present 10 representative problems. I will do this in two parts. So this is the pre-recording for the first half of the review. In the second half, in the next pre-recording, we will deal with greedy algorithms and divide and conquer. Okay, what is this midterm about? It's scheduled for the start of the 8-week, 100 minutes long. It is covering the first 9 lectures, so this is lecture 11. We introduced dynamic programming in the previous lecture. This will not be covered on the midterm because we have not collected homework on this. The material in this 8-week may have come very fast at us, and it might have been that you're not ready for the midterm exam. No trouble, don't hand in anything. Your 100 points will transfer automatically to the final exam. That's to be flexible. Now note that if the material is now looking very intimidating to you, the final exam covers everything. So there is still the hope we still have 4 weeks to catch up and to get somewhere um, in the course. But how are you? How do you know whether you will be prepared or not for the exam? Well, look at your homework exercises. So there is the textbook, there are the lecture notes, but actually the most important resource in this course are your own materials. The notes that you took when you were looking through the course materials, your solutions to the exercises. Make sure that you understand your mistakes and that you know when you solve a problem what to be mindful of. So in this 8-week course, we have covered the first 5 chapters in the textbook, but we have skipped certain subsections. So they will not be these topics, the algorithms in those subsections will not be on the exam. On the other hand, the review is representative. It's not exhaustive. So I can, in the time span of 100 minutes allowed in a lecture, I think I can only cover 10 problems. And also this then gives a wrong impression. I give the answers here and I will spend no more than 5 minutes for every answer. So it doesn't mean that something can be quickly presented, that it's also quickly solved. And this again may give you a misleading picture as we scroll through the slides. All right, this is an algorithms course. We use algorithms to solve problems, and we have solved many problems in this 4 weeks. Here are 13 problems. Some problems are covered in multiple lectures. We looked at, for example, connected components in graphs, which can be solved by graph traversals. We looked at the implementations and the applications of this connectivity, and we used it then again in a later lecture. So on the exam, you will be asked to to solve a particular problem on a small example. And that's mainly to get you into the mood of the algorithm to make sure that you know you understand the problem, you know the algorithm, but while you're running the algorithm, think about what you are actually doing. So because we are interested in the optimality, correctness, efficiency. We have algorithms, so we have actually more algorithms than there are problems. So we have the spanning tree problem, and we had 3 algorithms for this. In this review, I will cover only one algorithm because I only have that much time or that little time. Note that there will be multiple versions of the exam. So for, say, the spanning tree problem, I can very quickly come up with 3 different versions. So that also gives me the possibility to cover to give a broad coverage of what we have considered without having be too exhaustive as the exam is concerned. But I don't have to exhaust you for the exam. For example, on this review here, I will cover topological order, but I will say not much about breadth first search and depth first search. There are 3 versions on exam. On one version, you may have problems that are covered on the review, but you may have problems that are not at all covered on the review. So that's again a warning here. We covered first an algorithm, and then we are concerned with the efficiency, and then we study the data structures. Implementing an algorithm in this course means selecting the right data structures and reasoning, analyzing the cost of the operations on the data structures. So it is an open book exam. You have a lot of resources at your disposal, but you have to answer the questions in the context of this course. If there is a question asking for the implementation of an algorithm, you shouldn't come up with code. So that will give a very bad impression. Also, you will not be given much or any credit for verbatim copies, be it on the lectures slides, be it from the textbook. It is important that you can actually show and demonstrate that you can solve every problem within your own reasoning. All right, data structures used for implementing algorithms. We have covered data structures, the ones that we need in the algorithms that we have studied. Again, in the data structures, I teach data structures in a very hands-on manner with actual computer code. It's not important, or it's still important, very important that you can code, but for this course, we are interested in the properties of the data structures. Why and when are we going to use a matrix, an adjacency matrix, or an adjacency list representation of a graph is very important. Why certain data structures are having the properties that they do have. So the union find data structure is in particular covered on this review because it wasn't in the course when I taught data structures. Okay, that's the first 10 minutes on the exam, about the exam, also a little bit about this course on the design and analysis of algorithms. We restrict ourselves to discrete problems, so discrete mathematics is also very important. It will be coming at the start of the exam, second question, first question even. Although the master method we covered when we really needed it, when we were deriving the subcubic time for the analysis of Strassen's method to multiply matrices. Throughout the course, we presented many proofs. You will not be required to duplicate, to provide an actual verbatim representation of a proof, but you must be able to know what are the key arguments and to apply them. So what is not explicit on this slide here is that you know a proof by induction, you know an exchange arguments, as will become clear in the overview of the representative questions. Also know the terminology. So what is sublinear? So what is subquadratic? What is subcubic? No, you can of course start searching. If you have the textbook as a PDF file, you can search it, but you have to actually know the terminology already before you start the exam. All right, that is now the actual part where we are looking into representative questions. Again, the first set of slides is most important. Think about the problems first before you solve them. Make sure that you understand the question. All right, here is then the first question. We will look at an algorithm, look at a problem, and derive an expression for the costs. The problem we consider here has on input a matrix, a square matrix, where the diagonal elements are all non-zero because we divide by that diagonal element. The second input element is a vector of the same size as the matrix. And actually you can say, why is that the case? Because we're going to multiply the matrix with the vector. So that's a very short answer to this question. But let me go through it nevertheless. We compute n numbers and we want to derive a cost function, so you know it will be at least linear because that's the size of the output. Speaking of sizes here, you are asked to express the cost as a function of n, which is the dimension. If it is not specified, then it is the size of the input that we denoted by the capital N. So the size of the input here is the matrix. So the input size is quadratic in the function, in the dimension. So that means that it's already likely that you have a quadratic cost in the dimension. Just if you look at a problem, also rely on your intuition a little bit and be careful of this. So we will be deriving a cost and you have to be able to justify it, saying, I know it, so this has to be quadratic because you work on a matrix. That's not a good justification because we have cubic costs as well on a matrix. Okay, I will present now in the next slide my solution, which is a possible solution. I typed it up because I was now then thinking in that fashion. Now, on another occasion, I might have given a completely different answer. So know that there is not a unique solution to it. It is important that it is correct and that you have justified, provided a justification. So the justifications are just as important, if not more important, in this course. Okay, justifications can come in the form of a proof, a formal proof, but here they come in the form of a justification, of a derivation. So I will step by step derive the solution by interpreting the formulas. So I have here, when I look at it, I have one division, and the division stays constant, independent of n. I should say that there is this dot 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 notation here, which is here absent. So I started with I equals to n. So this is a algorithm that's backwards written. So the index I is the lead index, and you can see this also from the xi that we compute. So the algorithm is output oriented, so we are going through the output. We compute the output from the last element first. Note that what I do with the first step, I don't actually run the sigma, but I do one division. So it's important here that I have reinterpreted this algorithm. So this factor here, you could say I could pre-compute, make all the inverses of the matrix diagonal elements, and then multiply that. So that would be one division and one multiplication. This is fine. Here I have interpreted this as one division that I'm doing in every step. So I have n divisions. That's the beginning of my cost function. It's linear, very good. But then observe that the number of multiplication starts in the next to last element. We have one subdivision. The subtraction, the sub remains constant, so we have n minus 1 subtractions. We have an increasing number of multiplications and an increasing number of additions. So the expression at the bottom serves as a derivation and as a justification. It's not the final answer here because it's not counting as a function of the dimension. So there is still this letter k that is sitting into this. All right, let us then simplify, and I had to answer something in my second bullet point. So the elimination of the k, or the substitution for the big sigma, which is essentially still a for loop. So big sigmas in mathematics are translated as big for loops. And you can actually see that the big sigmas, the for loops here, they could have been an alternative answer to this question. You could have started with translating the mathematical expression into a double for loop. And then a double for loop runs n steps in the I, as we observed as well. And then we have the number of steps in the second for loop. In the body of the loop, we have a constant number of arithmetical operations, but we have this factor n minus I, which is actually the number of steps that you do in the innermost loop. So that's an alternative answer, which I'm here saying in words. I am in my presentation talking, and I'm presenting the answers on the slides, which are by necessity of my medium of the slides, they are very sparse. So there are words and sentences that are along with the answer. So that's also something to be mindful of. The second question concerns the measures of the cost function. So in some sense, it's a continuation of the previous answer. If we have an expression of the cost function, so the cost function can turn out very complicated, what is then the order by which we can judge the running time of the algorithm? Typically in this course, we are satisfied with the worst case running time, the big O notation, but sometimes we may be able to derive a big theta. So that's the third letter if your Greek is not that good. If you have a big theta, you have an upper bound and you have a lower bound. And the functions in this lower and upper bound, they are of the same order. Okay, let's practice this. We have two functions given. You see the second function is just a quadratic. And in some sense, you could see this big O, big omega, big theta is actually a way to simplify matters. And it's important to keep in mind also that we are interested in asymptotic costs. So the first function looks a little bit more intimidating. There is a constant sitting in there, there is a square root sitting in there. It's not entirely obvious that you can write one function in terms of the other. So the answers can happen here very quickly. Know that it's not the case that if you can quickly write true or false answer, that is also that you have to spend only the time it takes to write things. So again, spend some time on reflecting on your answer. And I will move also very quickly to these questions because they are very similar to each other. There are 6 different questions. I will spend a lot of time on the first question and then refer to the answers of the first question to justify all the other ones. But it's not that you should solve this question. The big data actually requires most work. Here is the answer to the first set of 3 questions. So and the answer actually is given by the simplification of the first function. We remember that a square root is a fractional exponent, n to the power 1/2. Adding 1 to 1/2 gives you 3/2. And this is the subquadratic time. So the exponent 1/2, 3/2, is larger than 1 but less than 2. So it is an example of a subquadratic time. And this is answering actually the question very quickly. But implicit here in the grows faster is that the threshold value for the n is there. So obviously if you plug in for little n 1, then 1 square is just 1, and that is definitely not larger than this 10 that you're going to find. So the threshold should be at least 10. So I'm saying this here now in words, and they complement the slides. So the narrative, if you are looking at the slides muted, if you just want to see the progression of the slides and not my explanations, then actually you don't have the complete answer. That's another point here. I am bounded by the medium that I'm using. What is written on the slides is not the complete answer. You also have to summarize the narrative of what I'm just saying. Okay, if we have solved the question 1, then we can very quickly go on to the other 2, because I just said that subquadratic is bounded by quadratic, but it's not the case that quadratic is bounded by subquadratic. Or you cannot use the quadratic as a lower bound for the subquadratic. So that's what the second statement essentially says. And I'm going to go even faster for the third question, which is kind of a misrepresentation in the sense that the big theta means that you have an upper bound and a lower bound. So to answer the third question, you have to do most of the work. But we have already shown that the quadratic is not a lower bound for the subquadratic f. So therefore, the um, answer to the third question is quickly given, but it incorporates the answers of the previous two. Okay, I will also go rather quickly over the next question. When the roles of f and g are flipped, I want to use the subquadratic time as a way, and actually now you would forget about the 10. The 10 is still there because I was copying my answer from the previous problem, but we would now typically in this settings come up with a quadratic function, a quadratic polynomial for g. And here is a variation. If you have n squared plus n, you would need to argue that this plus n doesn't really matter. So that was a property that we have proven, that if you have any polynomial, that only the leading term in that polynomial matters. If you have a question like this, feel free to refer to a property that we have covered in the lectures. Okay, 2 questions solved, and I'm about halfway in this lecture. I've solved the 2 questions in about less than 15 minutes, which is okay because I have prepared this a long time. If you need more time, please take more time. Do not take any answers because I say that this is the truth. Make sure that you understand what is true. Okay, the master method. We covered the master method when we needed it to justify subcubic time with the Strassen's method to multiply matrices. These are 3 questions because there are 3 cases. Again, there will be multiple versions of the midterm exam, and you may have one of the cases in the master method. It's important then for you to know that which case you're in. Here there are, for the review, 1 case, 2 case, 3 case. I'm also saying that you have to apply the master method. On the midterm exam, I may not do this. When do you need the master method? No, you don't. If you have given a recursion and you want an upper bound, then you may do this just by substitution or by unrolling, as we have done. So that's another variation of the same question. When can you apply the master method? Well, note that you see equalities, and that is necessary. That's necessary for a big data bound. If I'm giving you inequalities and I'm asking for a big O, then the master method may not apply because you will need to then show that your running time function t is actually an equal. And that may be a lot more complicated. Be careful here. So when we apply the master method, we have 3 things to consider, and this is typically done in a divide and conquer session. We divide our problems. N is kind of the size of the problem. We cut it in half. We cut it in 3 parts. And then we have to examine a number of sub-problems. It may be that we have to examine only one sub-problem, as is the case in the second question here. We may have 9 sub-problems. We may have 2 sub-problems. Dividing by a factor and the number of sub-problems, that's the first thing to look for. And then we have the combination cost, which is here n1 n log n. And that combination cost is going to determine whether, when you have the tree of sub-problems, whether the cost is focused in the root, is evenly divided among the nodes in the tree of function calls, or is dominated by the leaves, as is the third case. So the master theorem we have not proven, because it would take an entire lecture, and in this 8-week course there is not time, and there are very good discrete mathematics courses which treat this theorem in great detail. It is nevertheless most important that you can interpret the cases of the theorem, and also even more importantly that you know that you are in the case of the master method. On the midterm exam, I may ask you a recurrence for which the master method applies, but it may also be that I just ask you to solve a recurrence, and the master method may not apply because it's a less than or equal. I'm spending a lot of time explaining this question. It's also most importantly that you understand the question. Understanding the question is more than half of the solution. Okay, the solution is rather quick. If you understand how to apply it, we have 9 sub-problems. We cut it in 3, and the combination cost is linear. We evaluate the b log of a, the 3 log of 9, which here in this case ends up being larger than the combination cost f. Therefore, there is an epsilon that we can use to relate the combination cost to the cost factor that is given by the recurrence. In this case here, we have that the combination cost is actually starting to dominate. So the cost at the root is larger than at the leaves, because we divide by 3, divide so fast. So then the master theorem applies, and here it's kind of cruel. It's a short solution, but I cannot imagine that you have the master theorem right inside your head. So at this point you should actually have the theorem also right in front of you when you're solving this. Second case is a case where each time we cut our problem in half, and we have only one sub-problem to consider, and the cost of every combination is 1. So it's quite quick here, because it means that we are in the middle case. In the middle case is when the cost of all the sub-problems is proportional for all the sub-problems in the tree, which is actually here now a very simple tree. It's just one branch. This is the case. We have linear time. So in the notation of the course, some textbooks call it linearitmic, which I find a little bit strange. I still find it strange. That's why I remembered it. But I would say that it's almost constant time because the logarithm grows so slowly. We encountered this type of problem at the very beginning of the course, where we considered examples of efficient algorithms. Binary search is here the prototype. Sorting is so important is because searching in sorted data goes so fast. And after you have sorted, you have solved many problems, because the retrieval cost of an item is almost constant. Looking up things. Sort your course materials in preparation for the midterm. It goes often extremely bad on the midterm if you do not know where to look. Okay, solving recurrence, third problem, third case, third version of the exam. where we are seeing that we have two sub-problems after we splitted the problems in half, and we have to combine cost where we have to do some sorting, saying n log n. So in this case, actually, the cost of this method is dominated by the leaves in this tree of sub-problems. Then we can say that you see that if we compute the 2 logarithm of 2, we have a linear cost. And there is an epsilon. I didn't really specify the epsilon because even as the logarithm is growing slowly, it is not zero. So you can always find a minuscule exponent, a 1.1, so that cost actually will be a lower bound for the n log n. And that's probably the most complicated aspect of applying this argument in the third case. But here we see that even as the combination cost is dominated by the leaves, the total time is still n log n for this type of algorithm. Okay, I am getting into the last 15 minutes of the first half with two problems to consider. So we are still stuck in the first chapter of this course, even though we are covering a lot of important problems and aspects. So the Gale-Shapley algorithm is a very efficient and very simple algorithm, but what its importance lies mainly in the proof that if you do very little computations, you have a correct answer, a unique answer, and an optimal answer. So these were all very surprising aspects of this algorithm. And we also studied the implementation. So the second part of this question is just as important as the first part. So there's a lot of data to consider. So again, we have a labor market with 4 employers and 4 applicants. The employers have ranked their applicants in order of preference. So the first employer prefers applicant 1 over applicant 3 over applicant 2, and applicant 4 is actually the least preferred applicant for the first employer. Also, the applicants have a strict ordering for their employers. First applicant prefers employer 2 over employer 3 over employer 4 and does not really like employer 1 at all. That's the least preferred employer. Okay, we have the Gale-Shapley algorithm that we can run on this. It's an efficient algorithm, so the running will be over very quickly. Again, this is an algorithm that runs very quickly, but you have to be mindful and thoughtful that why it is so fast. And that's actually the second question, why you can do this so quickly. Okay, so let's run the example, and what we are actually going to compute is a set of matchings. So we have 4 employers, 4 applicants, and we will match every employer with an applicant. So we are listing the set of pairs step by step. So the answer is over in 5 steps. So the running time goes very quickly. The employers start to offer when they are uncommitted to an applicant, and the order in which this happens doesn't really matter. If it doesn't matter, you may as well use the preference, the ranking E1, E2, E3, E4. If you are interested in running this as quickly as possible, which we didn't consider, but you could take the so when it when you have an applicant that has an employer as its first choice and the employer has an applicant as its first choice. But here, first employer has a preference for first applicant. First applicant must accept because it has not received an offer. Same case with the second employer who offers to applicant 2 who is not committed. It starts to get interesting when we get to the third employer who offers to applicant 1. Applicant 1 is committed to employer 1, but employer 1 is the least preferred for applicant 1. So you can see that employer 3 is actually more preferred over employer 1. So therefore, the applicant 1 receives the offer of the third employer, and because applicant 1 prefers employer 3 over 1, it will break its commitment to the first employer and accept the offer of the third employer. Then the first employer is again free. We could have continued with employer 4. It most likely would not have mattered here, but we take the first employer that is free. Employer 1 has already offered to 2. Have already offered to 1, will not offer again to 1 because 1 will not break its commitment because it is committed to a higher ranked employer, 3. So we will offer to the next applicant, which is 3. Applicant 3 has not received an offer, and even though applicant 1 prefers employer 1, oh no, actually applicant 3 should be a very happy applicant. Its preference is indeed employer 1. Okay, then the last line is applicant 4 who receives an offer of employer 4. Employer 4 is that single employer who prefers applicant 4. Applicant 4 is not really a popular applicant, but applicant 4 has no choice but to accept. And one can verify that this is a stable matching. So this would be the follow-up question. So there is a follow-up question which refers to a data structure. How can we very quickly move on to the next applicant? So here you see step 3 and 4 were interesting. So also, how can an applicant quickly decide whether to accept an offer or not? So running the Gale-Shapley algorithm goes fast only if you have efficient data structures. We spent half of a lecture discussing the implementation of this algorithm, and therefore then proving that this is a quadratic running time algorithm, quadratic in the number of employers and applicants, or which is number 4 here. Okay, it's a very efficient algorithm. Here is the follow-up question. Here is one follow-up question. So there are at least 2 more variations of this. On the midterm exam, you may have exactly this type of question, which you have to demonstrate on another example. But you may have other follow-up questions. Prove that this is stable matching. For this example, show that the applicant can decide very quickly which employer to, which offer to accept or reject. So here is the answer. We have the employer preferences that are stored as matrices. So here I'm focusing in the example on the second employer. For every employer, we will have to decide very quickly to which applicant to make a next offer to. So that needs to be happen in constant time. You have data that can be accessed in constant times. Arrays are very good at that. So we will have one array. We have one array of size as many employers. The algorithm runs quadratically in the number of employers. So a linear data structure is fine because we have to initialize. So we initialize, so we start indexing at 1. We initialize every entry in that next array to 1 for every employer. And here on the example, when the second employer was again free, so it had offered to 2, but 2 received an offer from a more preferred employer and therefore rejected, broke the commitment to the second employer. So that's why it's important that the answer to the previous question was actually just 5 sets of pairs. And that's actually what you need to write. But actually the more complete answer is that you know while you are running the example, you should actually be telling a story to yourself. Why am I doing this now here? Last question that I will consider before this pre-recording ends, and that is question 5 on algorithms on graphs. So that was the topic of the third chapter. I will only give one question here. The alternative questions are graph traversal algorithms. Depth first, breadth first. Please do not neglect this. So here is the question. It's on topological ordering in a directed acyclic graph, abbreviated as DAG. So it's an algorithm that allows to order the vertices. It is also an algorithm to decide whether you do have cycles in your graph or not. So a directed acyclic graph is a graph without cycles. So here again, it's an efficient algorithm and we will run this on very small inputs, 6 vertices. And here you see that the number of edges is also relatively small. We could have many more. Is this graph a directed acyclic graph? You can't see it from the input, and that could be a motivation to run a direct acyclic graph. Direct acyclic graphs are very important in the analysis of parallel algorithms. As you could see, you could view every vertex as a task that has to be accomplished, and computing the directed acyclic graphs actually gives you an idea of the preferences of the order in which tasks needs to be accomplished. Is the topological ordering unique? And you could say, in some sense, when I run an algorithm is, as we remembered from the very first start, an algorithm is a sequence of instructions that is unambiguous and that can be executed, and it is finite in number. Of course, we have a unique answer, but that doesn't mean that the algorithm may compute one of the answers. Even if the algorithm will always give you the same answer, it doesn't mean that this cannot have, that there can't be choice. Justify that. Also, while running the algorithm, think about the second part. Okay, so here is the drawing of, I'm typesetting this very carefully. If I had to present this as my answer, I could only do one question on the midterm exam. Again, be mindful of this, that you know how to work efficiently in representing your answer. We have a directed acyclic graph if there is a source, at least one source. A source is a vertex that has only outgoing edges. An alternative follow-up question, if you still have topological ordering as this question, is how can you compute efficiently a source? And here I picked 0, but you can see that there is choice. So that's also already the answer, the fast answer to the second part. Is there a unique solution? Okay, how do you compute now a topological ordering? I have many slides and I have running out of time, so I can quickly scroll through this. 3 is the next source, 1 is the next source, 2 is the next source, and then I'm ending at 4. So the algorithm consists in selecting the next source and then removing the source with all the edges. So here I'm redrawing the graph all the time, but in your answer you can just cross things out. Know that don't wipe things out because you need to show all the answers. Just have a technique to wiping things out. Okay, so when you are at the base case only one node, this will be at the very end. So that's the last node in your topological ordering, and you insert the source to this. So going backwards, you can see how the topological ordering is constructed by essentially listing all the edges in a very structured manner. You have an ordering of the nodes from left to right. If you think about parallelism, then you see that you can start, if these 6 vertices are 6 tasks, you can start on the first task or on task with index 3 at the very same time. So this has parallelism in it. Directed acyclic graphs are an essential data structure in analyzing parallel algorithms. Topic that cannot be covered in this short 8 weeks. Okay, is the problem now unique? I will end with this. And the short answer is no, there might be more than one source. In the example, we could have started with 3 instead of 0. Now, there is always a yes or a no. So you could indeed say that there might be multiple sources, then multiple topological orderings, but the outcome of the ordering algorithm is unique. So in some sense, you can answer, so you will not have much, if any, credit to a yes or no answer, but it is in the justification. So you can say, you can interpret my answer here as saying in the first bullet point, yes, or no, there may be one more source. The answer is not unique. Or you could say, yes, there's always unique outcome, but I could have relabeled the vertices. And speaking of relabeling the vertices, that is then actually the next step, that you would relabel. So now we see the nodes from left to right, 0, 3, 1, but in some sense you could relabel vertex 3 becomes vertex 1. So in some sense we have the same graph many times, and I should stop here because I'm running over time. So I hope that this gives you an overview of what this course also is. So I have this pre-recording also intended a little bit as an indication what should you look at this course or not.